Module 4, The Basics of Test Methods. In this module, you will be able to define the functional testing. Compare the functional testing and structural testing. Demonstrate generation of test patterns for combinational, sequential, and scan circuits. Identify basic DFT design rules. Demonstrate the built-in self-test. Illustrate special tests such as for memory, cores, self-test, compression, IOs, etc. Identify the most common additional tests such as IDDQ and IO wrap tests. List out test escapes and their effect on test volume and product quality. Identify the basic diagnostic capabilities. Any kind of testing is always a matter of controlling the device that is being tested and observing its behavior. In the case of an SoC, we can only control the chip through the input pins and observe it through the output pins. We cannot directly access internal nodes to control or observe their states. For each fault, we need to manipulate the inputs to establish a circuit state that is both sensitive to the presence of the fault and will propagate the response to an observation point. Sensitive to the fault means that the circuit will produce different responses depending on whether the fault is present or not. We then compare the observed response to the predicted value. In this given example, the AND gate's output is stuck at 0. To observe this effect, both inputs should be at logic 1 of the AND gate, and to make that condition we need output of both the combinational block should be 1. To make this happen we will have to control the flops to get the required value at the input of the combinational blocks. This is how the test is problem of control and observation. For a modern chip, there are millions and millions of faults, so it can take a long time to compute all these tests, and can produce a very high volume of data, and take a long time to apply. Over the years, many simplifications have been adopted to reduce computation time, test data volume, and test time in manufacturing, and we will look at a few of these cases. Most, however, are buried deeply in computational algorithms, and do not change the basics of test generation, so we will ignore them. If you are already familiar with test and concepts such as scan, some of these slides may be review. We are going to be starting from the beginning, with functional test patterns. Functional patterns testing refers to generate all of the possible test vectors for all inputs, which can be fed into the chip, to test the chip, that it was properly manufactured. Originally, some subset of the chip verification patterns, functional simulation patterns, were used to verify that the chips had been properly manufactured. This makes a lot of sense. If the simulations are sufficient to ensure that the design is correct, then they should ensure that the chip was manufactured correctly. Unfortunately, that is not sufficient. There is still no generally accepted means for determining the completeness of functional verification. The advent, in the early 1970s, of the stuck-at-fault model and fault simulation, also called fault grading, found that functional verification patterns provided poor coverage, at best. Furthermore, as chips got larger, the controllability and observability of logic states within the chip became harder and more effort was required to create the functional patterns. It is not unusual, even with reuse, to see as much human resource used to generate functional test patterns as is used to design and verify the chip. Finally, it is extremely difficult to determine the root cause of, diagnose, a failing functional pattern. Still, functional patterns are still sometimes used as a supplement to automatically generated patterns. It is a well-known fact in the test industry that, if you can afford to do it, every additional type of test you can throw at the chips will detect a few defects that are otherwise not detected. Today, however, that usually means adding more automatically generated tests. Consider this example. In this circuit, total number of primary inputs are 12, and to test this circuit using functional testing method, we need to generate 2 to the power of 12 test vectors. This sounds exhaustive, right? This circuit is small. Suppose in today's chips, we need to generate millions of combination vectors to test the chip, and that functional testing will take years to test the complete chip, and which is not feasible practically. So, what is the solution then? Well, we move to structural testing now, and discuss this structural testing in upcoming slides. In order to achieve a nearly complete test of a chip, a simplifying assumption was made. The function would be ignored, and tests would be generated that verified that the behavior of the silicon matched the gate-level netlist. This is called structural testing. The list of faults is generated gate by gate. Picking one fault and generating a test pattern for that one fault required that signals be traced through the gate-level netlist to determine where to apply what values to chip inputs. Thus, the patterns test the chip gate by gate and interconnection by interconnection, rather than testing functions per se. In addition, the pattern generator only needs to understand the function of a small set of primitive logic functions, and, or, etc., not the function of the circuit as a whole. Thus, it can be automated. All modern test tools use structural testing for automatic test pattern generation, ATPG. Consider this circuit with 12 primary inputs and 2 primary outputs. Previously in functional testing, we saw that, to test this circuit, we will require 2 to the power 12 combinations, which means 4096 test vectors. But in structural testing, we will test every gate if it is working fine or not. Now, in this circuit, we have 9 2 inputs gates, 1 4 inputs, and gate, and 2 3 inputs gate, 1 is, and gate, and other 1 is, 2 cross 1 multiplexer. To test the 2 input gates, we will require 9 times 2 to the power 2 test vectors, which are total 36 test vectors, and to test 4 input and gate, we need 2 to the power 4, means total 16 vectors, and to test 3 input and gate, we need 2 times 2 to the power 3, which means total 16 test vectors. So in total, we will require total 68 vectors to test all the gates. Now you can see that this is the portion of the circuit, and by using structural testing, how many test vectors are reduced from 4096 to 68. Structural testing saves a lot of time and cost to test a chip as compared to functional pattern testing. This is the basic structural automatic test pattern generation, ATPG, loop. A single fault is randomly selected from the consolidated fault model. The test generator attempts to generate a test for that fault. If unsuccessful, the fault is marked as untestable and another fault is selected. If a pattern is successfully generated, it is passed to the compaction program. This program merges tests that are compatible, same clocking sequences, which we have not introduced yet, and no conflicting values on any input, into single patterns. Eventually, the compaction program determines that some set of patterns is as full as they are going to get, and passes them to the fault simulation program. The unspecified bits of each pattern are filled, usually with random data, and then the netlist is fault simulated with this pattern. First, the pattern is simulated with no faults applied to the netlist, and the results are recorded. Then the netlist is resimulated with each undetected fault, one at a time. The result of each of the simulations is compared to the results with no faults, and if there is a difference, that fault is marked as detected. Finally, the pattern is appended to the set of simulated test vectors if it detected at least one fault. So how do we generate test for a single fault? As mentioned before, a single fault is selected, usually at random. The cell pin with the fault is set to a value opposite of the fault, set 1. If the fault is A, stuck at 0, fault. Then, the back cone from this pin is traced, in order to determine a set of primary input values that will force this value. The other cell pins are set to non-controlling values, so a cell output will be different depending on whether the fault is there or not. The back cones for these values are traced to determine the additional primary input values needed to force these values. Then the forward cone from the cell output that is affected by this fault is traced to find a primary output that can observe the value. The back cone from that primary output is then traced to determine what additional primary input values need to be set to sensitize the path from the cell output to the chip primary output. Note that, for a dynamic fault, the test must also specify a specific transition, 0 to 1, or 1 to 0, on one of the primary inputs. If all that cone tracing fails to find a set of primary input values, that sensitize the fault and propagate its result to a primary output, then the fault is marked as untestable. In a well-designed circuit, this should not happen very often. Let's try an example. Here we have an AND gate that we assume is embedded in the middle of a combinational design. The fault selected is a stuck at 1 on the first pin of the AND gate. Stuck at faults are often shown on diagrams as shorts or vertical arrows. According to our algorithm, the pin with the fault must be set to a value that is opposite the stuck value. In this case, we have to set 0 to the stuck at input of the AND gate. The back cone from that AND gate input is traced, and a set of values are determined to the primary inputs that will force the pin to 0. This is called justifying the 0 value. The other input pins of the AND gate must be set to non-controlling values. In this scenario, we have to set the other input of the AND gate to 1, because if we set 0 to the other input, that 0 will not propagate the fault and will control the fault. The back cone from that input AND gate is traced, and a set of values are determined that will force the pin to 1. We now know that the output of the AND gate will be 0 if there is no fault present, and the output will be 1 if there is a stuck at 1 fault present. This is normally represented as a 0/1 value on the pin. The forward cone from that AND gate output is traced to verify that the AND gate output value can propagate to one or more primary outputs. The back cone from one of the primary outputs is traced, and a set of values at the primary inputs are determined that will sensitize the path from the AND gate output to the primary output. This is referred to as propagating a fault effect. This pattern is just one of many combinations that might test this fault. Cone tracing works best in a purely combinational circuit. Here is a portion of a circuit. The inputs and outputs could be scan flops or primary I/O, it makes no difference. The first step, of course, is to sensitize the fault. What values have to be placed on the inputs of the AND gate with the fault? Here is the answer, highlighted in red. Did you get the right values? Now, define a set of inputs and the resulting values on the logic feeding the faulty gate that will result in the correct sensitization values at the input to the faulty AND gate. There is more than one correct answer here. This is one of the combination. Here is just one possible solution for the test values on the faulty AND gate. On the upper AND gate input, with the fault, the required value of 0 means that both inputs of the OR gate must be 0, which means that at least one input of each of the AND to the OR must be 0. On the other input to the faulty gate, the 1 value requires that one of the OR gate inputs be 1, and we chose the AND gate input to the OR with the fewest inputs, since all of the AND gate inputs must be 1. Note that not all of the input values are specified. Now, what is the good machine, fault machine value on the faulty gate output, and what input values will propagate it to an output pin? Given the values chosen to sensitize the fault, the upper path could not be used to propagate the fault value to an observation point. The lower path could be used, and 2 additional input values were added to sensitize the propagation path. We now have a complete test cube for this fault. On typical SoCs, signals at logic gate pins will not be controlled or observed by the chip's primary inputs and outputs, but by scannable flip-flops, we can control and observe logic gate pins. The designs are not combinational now. Unfortunately, we don't build purely combinational chips very often. So how do we have to change the test generation for a single fault if there are registers in the design that control those cones we are attempting to trace? When backtracing runs into a register, then the test generator must set up another set of bits to cause the desired value to be captured in the register when the register is clocked. This must be done recursively until the chip's primary inputs are reached. All of these must be applied in sequence prior to testing the fault. Similarly, when forward tracing from the output of the gate, additional patterns and clocks must be applied to capture the observation in a register, and then to move it recursively through registers until it can be observed at a primary output. All these additional patterns must be applied after testing the fault. This results in a test for a single fault having multiple patterns and clocks. That makes it very difficult to compact tests for multiple faults. Alternatively, the test generator could retain the state of all internal registers and use that as a starting point when tracing. This makes all of the final test patterns dependent on each other, which is not desirable. To illustrate this, let's add only a single register in one of the back trace cones. We again apply the stuck at 1 fault to the first pin of the IN gate, and set the pin to the opposite value, 0, and backtrace. We now have assigned required values to a couple of primary inputs, and to the output of a flip-flop. When backtracing, and a flip-flop is found to control the path, then the test generator must recursively generate another pattern to set the correct value into the flip-flop before it can test the fault. To get that value on the output of the flip-flop, we need to set other values on the inputs of the flip-flop. A plus sign indicates a positive pulse, applied after the other inputs are applied. Backtracing from these values, we get another set of primary inputs, but these must be applied prior to the other inputs, controlling the IN gate pin. They are a separate pattern. When forward tracing, and a flip-flop is found to observe the results, then the test generator must recursively generate another pattern, to capture the value and propagate it forward. Again we apply the non-controlling value, to the other, and gate input pin, and backtrace. We determine the observable fault effect, trace it forward to possible observation outputs, and trace one of those back. We now have two patterns, that must be applied sequentially. In a realistic case, we would have indeterminate number. Application of a single fault test might require moving a finite state machine or counter from an unknown state to a known, desired state. That can take many patterns and clocks. So how are we going to resolve this? Well, we will discuss this in upcoming slide. Scan testing is done to detect any manufacturing defect in the combinational logic block. In order to achieve this, the ATPG tool applies input vectors at the scan chain's flops in an effort to excite each and every node within the combinatorial logic block. The way to eliminate the sequential nature of the circuit is something called scan test. All flip-flops in the circuit are modified so that they have two data ports. They are then connected so that, in scan mode, one data port is used to form all flip-flops into a set of shift registers between a set of primary inputs and a set of primary outputs. By setting the chip to this scan mode, the internal state of the chip can be controlled, from the scan-in pins to any arbitrary logic state with a single scan load. In addition, the previous internal state of the chip can be observed at the scan-out pins with a single scan unload. In effect, for test purposes, every flip-flop acts like a chip primary input and primary output. That is, after a scan, each flop is a control point, holding an arbitrary value that can be assigned by the test pattern generator. Then, only the application of a clock is necessary for it, to observe the test results at each storage element, which can then be scanned out. Using the flip-flops this way leaves only the combinational logic to be tested, which we know how to do. The cost is a minimal increase in the area of each flip-flop, and some increase in wiring congestion, both of which are taken into account in modern technologies. Scan is the fundamental concept, enabling automatic test pattern generation, ATPG. It is at the core of almost all automated test processes, including scan test for chip manufacturing, the IEEE 1149 family of board test standards, logic BIST, and test compression. All depend on a scan mode for test control and observation. How do we create this scan mode? First, all flip-flops in the design must be converted to an equivalent scan flip-flop that has selectable input data ports. A scan flip-flop is a muxed input D-type flip-flop. The scan multiplexer has two inputs, scan-in and data input. The selection of one of the inputs is done by the select line scan enable. One of these ports is used for functional operation, the other for scan operation. There will normally be a test control signal that switches the circuit between the scan state and the normal functional state, called scan enable by convention. Traditional flip-flop which captures its input on the rising edge of its clock. The simplest way to do this is just add a 2x1 multiplexer on the data input of the flip-flop. The multiplexer is controlled by the scan-enable test control signal, and selects either the functional data input or the scan data input. The differentiation between the two is a matter of convention. To eliminate the sequential nature of the circuit, we do the scan testing. All flip-flops in the circuit are modified so that they have two data ports. They are then connected so that, in scan mode, one data port is used to form all flip-flops into a set of shift registers between a set of primary inputs and a set of primary outputs. Here, we will discuss how to do the scan testing to test the design. Step 1 is to make the connections from one flop to another flop in a way so that every flip-flop is independently controlled and observed and behave like a shift-shift register chain. Second step, to change the mode of the design from functional mode to scan test mode with the help of scan enable pin and load the test stimulus. Third step is to again change the state of the design from test mode to functional mode and observe the response of the flops at primary outputs. Step 4 is again change the state of the design from functional mode to test mode and unload the test stimulus. That is how we do the scan test step by step, and we will discuss every step in detail in the upcoming slides. Here we show, in red, the additional connections required when converting a conventional flip-flop design to a scannable design. The scan input of each scan flip-flop will be connected to the output of one other scan flip-flop, or to a scan-in-chip test input. The output of each scan flip-flop will, in addition to its functional connections, be connected to one other scan flip-flop, or to a scan-out chip test output. This forms one or more scan chains. The scan-enable test control signal must be wired to every scan flip-flop. The clock is not modified for test, but must be able to be controlled from the tester. There are other architectures for converting flip-flops and latches to a scan elements, but the basics remain the same. The ATPG program treats each scanned flip-flop as both a primary input, meaning that the ATPG can set each flip-flop to an arbitrary value, and as a primary output, meaning that the ATPG can observe any value captured in each flip-flop. All that is left to test is the combinational logic, shown as the blue cloud. Let's take a look at how this is done: loading the stimulus, capturing the circuit response, and unloading the responses. Here we show just the logic in the design needed to load the scan chains with control values. The scan enable pin is set to the scan value. Then the stimulus data, calculated by the ATPG program, is supplied serially at the scan in pin, 1 bit per clock pulse. The clock is pulsed the same number of times as the length of the scan chain. At the completion of this operation, new stimulus data will have been loaded in each and every scan flip-flop. The scan-enable test control input is set to the functional operation state, and all functional primary inputs are stimulated. All of the control values specified by the ATPG algorithms are now in place. The clock is pulsed as specified by the ATPG programs. This exercises the logic and captures the values that result into the flip-flops. All functional primary outputs are observed, but the values captured in the flip-flops have not yet been observed. To unload the captured responses, the scan enable pin is again set to the scan state. The clock is pulsed the same number of times as the longest scan chain, and the results captured into the flip-flops are observed at the scan-out pin, 1 value per clock pulse. In reality, the loading of the stimulus for a test can be done at the same time as the unloading of the captured responses of the previous test. This is referred to as overlapped scan, and is the normal way of applying and observing scan tests. To use scan, we have to give the test pattern generator the correct control and clocking sequences at chip primary inputs to perform a scan. It then generates a few patterns to verify that the scan chains themselves work. These few patterns will actually pick up several % of the total faults in a typical chip. One of the simplifications used to reduce the test generation computation time is that, after these first few patterns, the actual scan is never simulated. The desired control values are loaded directly into the scan flops, and the values captured in the scan flops are directly observed by the fault simulator. We can now proceed with the ATPG loop we discussed earlier for the combinational logic tests, with the addition that the test generator must set test control primary inputs and pulse the clocks as required to launch the scan data and launch transitions for dynamic tests, and to capture the design response into the observing flops. While the discussion has assumed full scan, all flops are in the scan chains, the combinational test generator will tolerate a small number of non-scan flops, particularly if there is no feedback around the non-scan flops. The more non-scan flops in the design, the higher the computational time and number of test patterns it may take to achieve the desired fault coverage. In addition, when there are larger numbers non-scan flops, sequential test pattern generation may be used to supplement or even replace combinational test generation. There are two main categories of design rules: those that affect the ability to test certain faults, or that affect test coverage and time, and those that are required for the proper operation of the scan chains. If these design rules are violated, the scan chains will not operate properly, and the chip cannot be tested, so exceptions are rare. Rules that guarantee scan chain operation. Normally no exceptions. Scan chains must originate at a chip input and terminate at a chip output. The chains may not be broken. This ensures that the state of all internal storage elements may be controlled and observed. In an environment where multiple clock domains exist, and flip-flops may be clocked by either edge of the clock, retiming latches and scan chain ordering must be used to ensure that the scan will work robustly. Changing any of the chip test control inputs may not cause the state of storage elements to change. This ensures the integrity of the scan data. This is why asynchronous set and clear signals cannot just be negated by scan_enable. Finally, for mux scan type designs, the delay from scan element to scan element in a chain must exceed the sum of the worst case clock skew plus the scan element hold time. This ensures that the data will propagate properly through the scan chains. Where this cannot be guaranteed, retiming latches are added to the scan path to provide controlled timing. These are typical of the rules required to ensure operation of the scan chains, without which the chip cannot be tested. Of the rules that affect test time, data volume and cost, some are higher priority than others since they may, in certain cases, cause the test generator to generate invalid test patterns. Strong structure verification rules checking will detect almost all structural, non-timing, rules violations. In certain situations, the user may choose to ignore the violation, but should ensure that the condition will not, in fact, create bad patterns. Otherwise, time to market will be adversely affected by first silicon debug of patterns, something we believe should not be necessary. First among these design rules is no combinational feedback. In effect, combinational feedback creates unclocked memory in the circuit. Its state is not determined solely by the circuit inputs. This effect is not modeled in the test generator, which assumes that all of the combinational logic starts at an unknown state for each test pattern. If logic cannot be modeled as gates, it cannot be understood by the test generator. IP that is provided as a black box with test patterns are acceptable. Clocks may not be used as data inputs to flip-flops. The timing of the clock pulses is different from the timings of data inputs. Finally, if there are any paths that are slower than the intended tester cycle time, the test generator typically cannot recognize the situation and determine the correct capture value. The remaining rules only affect test coverage and cost. The first is that there be no three-state or other multiply-driven nets, including transmission gate, one-hot, logic. If the logic guarantees one and only one enable will be active at a time, this rule may be violated without problems. Test structure verification can check for such mutually exclusive control or correlation information can be added to prevent the test generator from creating patterns with orthogonal drive after the end of the scan. There should be no visible X-state generators in the logic. While the test generator will simply record the X-state in the responses, a chronic X-state generator will block the testing of some faults. Non-scan storage elements, including memories, are assumed to contain X at the end of scan. Thus, they violate this rule and generally make it difficult or impossible to test many faults. For memories and other X-state generators, the situation can be corrected by designing a wrapper that observes all inputs and controls all outputs, fully isolating the generator from the rest of the logic. The chip must be scanned for the longest chain. Unequal scan chain lengths waste space in the scan buffers for the shorter chains and take longer to perform the scan. With modern tools, scan chains should be balanced within a few %. Answer the following questions. At this point, we've covered how the tests for each fault are generated and the role that scan plays in making that happen. The next step is to compact all these individual tests into a smaller number of test patterns. Test for single faults may be merged if they do not have conflicting values applied to the same primary input, and if the launch and capture clock and control sequence is the same. The scan sequence is always the same, by construction. The compaction program maintains buckets of patterns with compatible clocking and keeps track of how often a new test is merged into a particular pattern. Based on user-selectable criteria, the program will decide when it appears that no more tests are merging into a pattern. The remaining unspecified bits of the scan load are filled, usually with random data. The pattern is then passed to the fault simulator. In the fault simulator, the good machine response, no faults applied, is compared to the response of the circuit, with each untested fault applied, one at a time. When the responses differ, the fault is marked as detected. For an average pattern of a large chip, the density of the specified bits will be less than 2%. There will be a few patterns in the set that have specified bit densities in the 20% to 90% range, and many that have densities well below 1%. The first few patterns will have very high density and test many faults. Here we show the values to be loaded for a single pattern into 3 scan chains in a chip that is being tested. The test generator creates a test for fault 1 with just a few bits specified, and this is passed to the compaction program. Perhaps this is the first test cube, as tests for single faults are called. Let's say this test cube doesn't fit in any existing vector, so the compactions program creates a new vector that initially contains just this one test cube. Tests for additional faults specify additional bits as they are merged. Note that the different tests may share some specified bits. Here you can see that fault 2 and fault 3 are sharing the specified bits. After some time, with no additional tests merging into this pattern, it will be filled and sent to the fault simulator. Note that most of the data that will be scanned into the chip is fill, usually pseudo-random data. This low density of specified bits has 2 important consequences. Most of the test data is fill, and many of the faults that will be detected in the fault simulator will be detected by this fill data, especially pseudo-random fill. This happens because the fill accidentally sensitizes and propagates a fault effect. The low density of specified bits allows us to compress the test patterns. The patterns will be decompressed and filled by on-chip logic. Compression is actually performed as part of the compaction of the individual tests, and details are covered elsewhere. However, compressed test patterns may have average specified bit densities in the 20% to 80% range, instead of the 1% to 2% range. Detection of faults is not a linear process, in terms of the number of test patterns versus coverage. As shown, coverage, the percent of faults detected, starts with the results of the test of scan chain operation, and grows rapidly at first. But it quickly rolls over, as the easy-to-detect faults are all detected. Then coverage grows slowly until all testable faults have been detected. Most of the patterns are in what is often called the tail of the curve, the area where coverage grows slowly. There is an engineering trade-off here, where drastically reducing the number of test patterns, and therefore, the cost of test, reduces the coverage only a little. But system cost can build up rapidly, especially in complex systems, due to test escapes. The length and slope of the tail are heavily affected by a number of factors. One that is under the control of the chip design team is how well they have followed the design rules. Compliance with the design rules will often have significant impact on chip quality, manufacturing test cost, system test cost, field returns, and customer satisfaction. Conclusion. The last few percent, or fraction of a percent, of coverage require the most patterns. Built-in self-test, BIST, is a type of structural test method in which logic adds to the chip in such a way that chip tests itself to its own operation. Two main types of BIST are memory BIST, MBIST, and logic BIST. Now we'll take a quick look at some of the other test methods, starting with built-in self-test, BIST. In general, BIST simply means that the test stimuli is generated on chip, the responses are captured on chip, and the test itself is controlled on chip. The stimuli may be deterministic, or pseudo-random, and the responses are normally compressed to a pass-fail value which is checked at the end of the test. Otherwise, all of the concepts and rules discussed before still apply. There is a lot of appeal to the idea of a chip testing itself. The test can be used not only for chip manufacturing, but for board, system, and even field testing of the chip. We see BIST used in automotive components for in-system, or at the time the car is turned on. The trade-off is the silicon area consumed by the BIST circuits and the coverage achievable with on-chip stimuli generation. There are variations that give the tester more or less control. The onboard controller may need nothing more than a clock and a go test signal, or the tester may have to program the test first, or the tester may actually provide the entire control function, possibly on an override basis. Testing of large, very regular structures, particularly memories like SRAMs and DRAMs, is one area where memory BIST shines. The deterministic patterns, in terms of address, data in and data out, needed to fully test RAMs are well understood and reasonably easy to implement in silicon. As a result, virtually all RAMs instantiated in chips today have a memory BIST, MBIST, controller, built into or instantiated with the memory. Some of the RAMs are designed with extra rows or columns of memory cells, so that when a defect is discovered, the defective memory cells may be switched out, and the extra memory cells switched into their place. The MBIST will provide the row, column information or failing bitmap to support this. ROMs, while regular structures, are normally just checked with a simple checksum of the contents. To test digital logics in chip or part of a circuit logic, BIST is used. Best chip test for board, system, and field. Logic BIST uses a pseudo-random pattern generator, PRPG, to generate scan test stimuli, and a multiple input signature register, MISR, to compress results. PRPG usually built from a linear feedback shift register, LFSR, other possibilities such as cellular automata. Usually added to chip, could be built from existing scan chain elements. It is relatively hard to get good coverage, due to lack of intelligence in pattern generation. Because test points may be inserted in logic, or sometimes no X states may be captured. Another common methodology for reducing test time is test compression. This is motivated by the fact that, for large chips, the test data volume has become too high to fit on many testers, and the test time has driven test cost up to where it almost equals the cost of manufacturing the chip. The test structures used by most compression schemes look remarkably similar to logic BIST, with the biggest difference being that the generation of the stimuli is controlled by the tester. This preserves the very high coverage expected during chip manufacturing test. ATPG generates the tests for each fault as normal, and the compaction program creates the compressed test patterns. Fault simulation simulates the decompression circuits, marks off detected faults, and adds the compressed response data. The goal of test compression is to reduce the data volume and test time to a few percent of the original, without compression. The ability to compress test data depends on all those unspecified bits in the typical ATPG test patterns. By adding logic on the chip that decompresses the test data with a known algorithm, then the single fault tests can be merged, using the inverse algorithm to create a much smaller set of test patterns. This depends on the compression-decompression algorithm being linear and reversible. The decompression could be combinational, but most algorithms assume a linear sequential circuit very similar to the pseudo-random pattern generator used for logic BIST. Compaction is the process of merging single fault tests, and traditionally assumes no decompression on the chip. That is, there is one bit in the vector for each scan cell. Compression assumes a specific decompression circuit on the chip and packs the specified bits for the single test faults into a much smaller data structure. Test time is dependent on both the data volume and the length of the longest scan chain on the chip. For normal ATPG, the length of the scan chains is set by the memory behind the pins on the tester as well as the design's pin limitations. Since the decompression of test data is done on chip, many more scan chains, correspondingly shorter, can be used. So savings in test time are realized by increasing the number and decreasing the length of the scan chains. For diagnosing failures, there is normally a traditional scan mode built into the chip to allow the uncompressed responses to be recovered. This supports the full diagnostic capability. In addition to static and dynamic tests, we have been discussing, there are other types of tests that must be generated in order to complete the manufacturing test of the chip. The common ones are IDDQ tests, which measure supply current as the faults are stimulated. I/O wrap tests, used to test uncontacted drivers and receivers at wafer test. I/O parametric tests used to verify that drivers and receivers meet their analog specifications for voltage and current during module test. After all that additional tests, the patterns are all packaged together and meet the chips and modules at one of these testers. The chip or module sits in the middle of the test head, hanging outside the rack of electronics. The result is that some modules will fail and some will pass. For some number of chips that are tested, some will fail test and be rejected, and the others pass and will be shipped. But tests are not perfect, so some of the chips that pass test will, in fact, be defective and will not work correctly in the system. These parts are called test escapes. Obviously, we want to make this group as small as possible. So, how good are the test patterns? How do we measure the quality of the test results? The normal measure of test quality is the fault coverage. This is simply the percentage of the faults that are tested. But what does this really tell us? If the calculated fault coverage is 99%, does this imply that 1% of defects will not be detected, and 1% of the passed chips will be defective? Not necessarily. Many defects will cause multiple fault behaviors, and may affect multiple nets or transistors. This means that the defect may be detected even if only some of its possible incorrect behaviors or faults are observed. As a result, the percentage of escapes is typically less than the percentage of untested faults, but the exact ratio is not typically known. The chart shown, on a log-log scale, is for a particular mature bipolar technology, and illustrates the fact that the percentage of escapes is less than the untested fault coverage. For this technology, it is lower by a factor of 5 to 10. So, is high fault coverage not important? Not necessarily. Escapes result in incorrect behavior at the board, system, or field level, depending on when it is detected. Defective behavior at these points will cost significantly more than just the cost of the chips themselves. The impact of escapes depends on both the complexity and the quality requirements of the system. It should make sense that a high percentage of escapes will have less impact on a low-cost consumer product, with only a few chips than on a complex, expensive system containing many chips. In this plot, we take the escape percentage for 3 different fault coverage values from the previous chart, and calculate the percentage of defective systems that would result just from bad chips. Plotting this against the number of chips, we get the lines shown. Clearly, for this technology, chips intended for complex systems with high-quality requirements may need to be tested to better than 99% fault coverage, despite the very low percentage of escapes implied. Chips intended for simpler systems with lower quality requirements, it costs less to throw away bad systems, may be able to get away with fault coverage in the mid to high 90s. To diagnose why we are getting the failing chips, the tester needs to follow few steps to trace the reason why the chips got failed. First, assume the defect in the logic, Then trace back through sensitized logic. After tracing back to the sensitized logic, observe the miscompares, if any, and finally analyze the miscompares. Here is an AND gate, and we'll assume that the defect is causing its one input to behave as A, stuck at 1. But we don't know that yet. All we know is that we have some miscompares in a specific pattern. First, we apply the failing test pattern stimuli to the circuit. The simulation of the pattern will apply controlling and non-controlling values to input pins throughout the circuit, including the two inputs to the AND gate shown. The output miscompares are traced back through sensitized logic, creating cones of logic that could have caused each miscompare. Assuming only a single defect, it must be in the common area, covered by all the miscompare cones, the central overlap of the two cones including the AND gate. The non-overlapping areas are pruned from the list of possible faults. Some of the outputs that were correct, the observed value and predicted value matched, can also be traced back through sensitized paths. These essentially exclude logic from the area that could create the miscompares, as shown by the two outer cones that do not include the AND gate. The process continues, gradually reducing the list of possible faults. If necessary, the test pattern generator can be used to create special patterns that sensitize some of the possible faults and not others. These patterns are applied to the chip, and the results are added to the analysis. The actual algorithms are much more sophisticated than this, and can handle multiple simultaneous defects, use multiple failing patterns, and so on. Specifically, if you assume that there could be multiple defects, then all of the faults in any failing cone must be considered, not just the overlaps of the cones. The list of possible faults is prioritized, using fault simulation of the candidates. But this should give you the list of how the process might be performed. Finally, once we start getting failing chips, we want to know why they failed. So what can we do? Each miscompare contains the information, which scan chain, which scan cycle, to uniquely identify the flip-flop that captured the incorrect value. Simulation and tracing algorithms use this information to generate a list of possible causes, called a callout list. The test pattern generator can generate patterns to differentiate between the possible faults. Once the most probable logical faults are called out, they may be mapped onto an image of the chip, mapping the fault information from the logical to the physical domains. This provides a starting point or points for the failure analysis team to start investigating. Optical inspection of the identified area is a frequent first step, as many defects of the wiring will be visible. If analysis tools such as electron beam or pica, picosecond imaging circuit analysis, are to be used, the test generator will create a small set of patterns that will continuously re-stimulate the suspected fault in a tight loop. This will allow these tools to build up an image of the behavior over many repetitions. It can be very valuable to monitor the types of defect that are occurring. This can identify weaknesses in the design of the technology cells and acts as the ultimate monitor of the technology process and manufacturing line. If the defects are dominated by one type of defect, for instance, it is probable that the process can be adjusted to eliminate most of that defect. This is how the yield of a technology process is improved over time, holding down the cost of chips and enabling Moore's law, as well helping us sort out good chips versus bad chips. For more content and learnings, visit Cadence support site. To enroll for the courses, visit www.cadence.com. Click on the Support tab and open the Digital Design and Sign-Off Training section to enroll for the courses. Click on the Digital Design and Sign-Off Training section. Choose the course from the respective technologies and enroll for the course. Click on Enroll icon to enroll for the respective course. Thank you.